So we sort of did the investigation before, and we should have ended up with this fundamental theorem of calculus, which is that if we have like a definite integral between a fixed value and x, we can come up with this area function, which is the antiderivative of our function in our integral. So f of x is the antiderivative with our upper bound input minus whatever our lower bound is inputted in there. Now, for this particular option, we've got this is a fixed point and this one's moving along there. So this f of t, this is a notation that just shows us that it's the antiderivative. So fundamental theorem can be stated in below forms. For a continuous function f of t, if we define the signed area function from t equals a to t equals x as the area function of x with input value x, then it goes from this fixed point, the x value can move, they're pretty much saying the same thing, then the derivative of the area function. So if we take the derivative of this, it's the derivative of this integral, which is the derivative of the antiderivative of f of x minus the antiderivative of the f of x function with a put in, which would just give us back our original function, which is the derivative. This is because the derivative, or dx of f of x equals our original function, and the derivative of f of a is going to be 0. Now, more commonly, we would just use this notation here, which is if we have an integral from one bound, a lower bound to an upper bound below a function, dx, it's going to be the antiderivative of the upper bound minus the antiderivative of the lower bound. I've just got a note here, area under a curve should be represented in the simplest unit mixed fraction where possible. So let's do an example of this. So use fundamental theorem to find the area between the x-axis and y equals x squared from x equals 0 to x equals 1. So we're looking here at the integral will be the area here from 0 to 1 of x squared with respect to x. Now that's because we've got the x-axis there. So what we do here is, I'm just going to double check. So they've done it a little bit different here. So I'm going to follow what they've done. We will see a slightly different method in a bit. So we've got, if f of x equals x squared, then the antiderivative of this, which we've talked about, has to have a derivative of x squared, which means we're going to be looking at x cubed, and it has to have a third there. Now that means that this, I'll move this below here. So the integral of this is going to equal the antiderivative of the upper bound minus the antiderivative of the lower bound. Now we've got our antiderivative here. So what this means is we're going to have 1/3 1 cubed minus 1/3 of 0 cubed, which means this is just going to equal, the area of this particular thing would be 1/3, and it's just going to be units squared. So that would be our shaded area. This would be our area from 0 to 1 here, and that would be this shaded area here. The next one here, we've got another function here. So we've got y equals x squared. So we're considering the area here of square root x with respect to x, and it's between 1 and 9. And so in considering this, if f of x equals x to the half, we're looking at the antiderivative of this. So the function before this, which would be f of x equals x to the 3 on 2. And now because of if we took the derivative of the 3 on 2 here would come out the front. So we need something to multiply with that 3 on 2 to give us 0. So that would be 2 on 3. Now I'm just going to actually check this one because of, it's always good to check if we can. So the derivative of the antiderivative should give us our original function here. So this would be 2 over 3 times by 3 over 2 x to the half, because that's 3 on 2 minus. They would cancel perfect. It all works out there. I'm just going to get rid of those crosses. So that's a big tick. Okay, so that means the integral here would equal f of x minus, not f of x, f of 9 minus f of 1, which means I'm going to have my antiderivative here, which is 2 over 3, and then this is going to be x root x because of this form here, 3 on 2. That's what it looks like in this power. I should have put that. Let's just move that. Run out of room. Let me just rearrange this a little bit for us. Okay, and then that would be 9, and that would be 1. Okay, so that means that using that form there, we're going to have 2 over 3, and it's going to be 9 square root 9 minus 2 over 3, and we've got 1 square root 1. This is going to equal 2 over 3, 9 times 3 minus 2 on 3. All right, which is going to equal, I'm just going to pull out the common factor of 2 on 3. 9 times 3 is 27 minus 1 equals 26 times 2 is going to be 52 on 3. And if I put that in my calculator, 52 divided by 3 equals 17 and 1/3 units squared. So that's how we use this fundamental theorem of calculus in that space. Now I'm going to keep rolling through just so we can sort of do this. So these are some of the properties of definite integrals using the fundamental theorem of calculus. So this one here, if we have the same bound, if we think about this, this is going to be f of a minus f of a, which is just going to equal 0. So that one there, it's, if we were thinking of it geometrically, it's going to be, if I have a function here, the area, it's got no width. So that's why this one always is going to equal 0. You can't have an area under a curve if you've got the bounds of the same place there. This next one here, it talks about if we have a constant function here. So this one here, if we have the constant function, well, the constant function here, if we, and I'm just going to double check. So this one here, if you think about it, we're going to have f of b minus f of a here. Now, because the antiderivative of a constant is going to just be, well, k, I'm just going to use x. This would be kx, would be the antiderivative here, minus k. So the antiderivative here, let's move this up, stuff that up. Okay. So here, the antiderivative of a constant function, if we have f of x equals a constant, then the antiderivative of that is just going to be kx. So in this space here, we're going to have k times b minus k times a. We can take out the common factor of the constant and have it like this, which is pretty handy there. So that form makes it easier to take that area. And if we were thinking about this geometrically, again, if we have a constant function, it is just a straight line, which means we're going to that's going to be the height of this, and then this value here would be b minus a, which is b is our upper bound, a is our lower bound. Okay, next one here, we've got, if we have the integral from, so this one here, this top form, we would rewrite this as b minus a. Hang on a sec, have I written that the right way around? They've tricked me by putting it the wrong way around. So in this one here, you notice they've swapped the upper bound, so they've done a here and b. Now, if I was to multiply this whole thing by -1, it would be negative, or if I pull out a common, like if I pull out a -1, then we would have negative f a there, and then So this form here, I'm gonna rewrite this here. So if this was -1, so this is the left-hand side, this right-hand side here would be f of b, because that's the upper bound here, minus f of a. We should see here, I'm just going to highlight that one, and the b's. I'm just highlighting the b's so we can sort of see this. If I multiply that out, it ends up being negative f of b plus f of a, which you'll notice here is exactly the same as the first notation. So what this is actually quite significant. It means we can sometimes swap the bounds. It allows us to simplify a little bit easier later by doing that. It's a way to solve integrals more efficiently. Our next one here is if we have a constant times a function, we can factorize the constant out. So this form here will be k f of b minus k f of a. And this form here is we've pulled out the common factor of a, and then we've got f of b minus f of a. This one here, again, I'm going to actually highlight this one in yellow because this one is massive in simplifying fractions, so please take note. Now, this next one here, you notice we've got these two separate integrals, but the upper bound is the lower bound of the other one. So upper, and that's the lower. Now, if I was to draw this, I'm just going to do a rough drawing. Okay, if we have A here, B here, and C here, if I was to, this integral here represents the whole area. Okay, and this would be the area, let's just call it area of A. So this is that, not A. Let's just pick, I'll have to use a highlighter. So this is the area, I'm just using pink around this. That's this first one here represents that area. And then this next one represents this one here. So when we have those bounds are the way they are, it actually means we can add them and we can consolidate to one integral. So this makes it a lot simpler. This next one here is just a notation we should know. So the property here is quite handy. If we have two functions added together, so if you think about you've got an x cubed plus let's just go e to the x, you can actually separate it into two separate integrals here. So it allows you to break these things up. So in this space here, you'd be looking at, this would be f of b plus f of a. Now, it says plus or minus because we can do either one. I'm just going to use a plus for the example here. So f of b, let's just do f of b plus g of b. That should be a capital for an antiderivative. G of b minus the lower bounds here, which is going to be f of a. I'm just going to have to put a big bracket, plus g of a. So this would then be f of b minus f of a plus g of b minus g of a, which if you look at is the same as if we'd done them as two separate integrals there. So that's the property of integrals. So that's quite important. That one there really helps us out. All right, thanks guys.